Buckle up, everybody, because today we're taking a deep dive into the world of hydrogen rocketry.
Ooh, hydrogen rocketry.
Yeah.
I like it.
We're talking super cold fuels, fiery plumes, and how we use the simplest element in the universe to, well, reach for the stars.
It's kind of mind-blowing when you think about it that way.
It really is.
Using something as cold as liquid hydrogen to create so much heat, so much power, it's a trip.
It's a total paradox.
Right.
But before we get to the flames and the nitty-gritty, let's break it down.
Okay.
What makes liquid hydrogen so perfect for space travel in the first place?
Well, for rockets, it all boils down to efficiency, right? And in rocket science, we measure that using something called specific impulse, or ISP.
ISP.
Yeah, you got it. Think of it kind of like miles per gallon for your car. But instead of measuring distance, it tells you how much thrust you get out of each unit of fuel.
So higher ISP equals a more efficient engine.
Bingo. You got it.
All right, so where does hydrogen fit into all of this?
Hydrogen, when you mix it with a liquid oxygen, gives us the highest ISP of any chemical rocket fuel we know of.
Really?
Yeah, it's the real deal.
Wow.
That means we can send heavier payloads further into space, all while using less fuel compared to, say, those old kerosene-based rockets.
So efficiency is the name of the game.
Efficiency is key.
It's not just about raw power. It's about getting the most bang for your buck, so to speak.
Exactly.
I've got to admit, though, picturing this super cold substance, colder than the surface of Pluto, bursting into flames, it's quite the visual.
Oh, yeah, it's wild.
It is.
And getting that liquid hydrogen to light up, to combust efficiently, that takes some next-level engineering, let me tell you.
Yeah.
It's not as simple as just, throwing a match on it.
Right.
It's about creating this perfectly controlled, sustained explosion that gives us thrust.
So how do they do it? How do engineers even begin to work with something so, I don't know, volatile?
It's a challenge, for sure.
Yeah.
Our sources mention things like special alloys, coatings.
Right.
They had to figure out how to deal with the extreme cold.
Because it's not just about the fuel itself.
No, not at all.
It's about the materials, the entire system.
Absolutely. You see, one of the big hurdles with liquid hydrogen is that it can make some metals brittle.
Oh, wow.
Imagine your spaceship crumbling like a cracker.
Not good.
Not ideal for a long trip through space. So early on, a ton of research went into figuring out what materials could withstand those super low temperatures.
They had to almost reinvent the wheel,
Yeah.
or in this case, the rocket.
In a way, they did. And you know what? That spirit of innovation, it's still going strong today.
I bet.
We're always on the lookout for new materials, new designs, all in the quest for even more efficient hydrogen-powered spacecraft.
It's incredible the ingenuity it takes to use something so counterintuitive, so potentially dangerous, to achieve spaceflight.
It really is.
It's like they looked at something that seemed impossible and said, challenge accepted.
Exactly. I mean, it's not just about the materials themselves.
Right.
To really squeeze every ounce of performance out of these engines, scientists had to get down to the nitty-gritty, to the heart of the flames.
Okay, so we're talking
We're
about
talking plasma physics.
plasma physics.
Yeah, it sounds complicated, but it's actually pretty cool once you wrap your head around it.
Okay, break it down for us.
So those rocket plumes that we see, they're not just fire.
Sure.
They're actually superheated, electrically charged gas. That's plasma.
Oh, wow.
And by studying how this plasma behaves during combustion, scientists can fine-tune engine designs for, you guessed it, maximum efficiency.
Hold on. So you're saying by looking at the light and heat coming from the engines, we can actually figure out how to make them better?
That's exactly what I'm saying.
That's wild.
It's like we're looking at an X-ray of the combustion process itself, seeing all the inefficiencies, the instabilities, the areas where we can tweak things for better performance.
It's amazing how we've gone from just, harnessing fire to harnessing plasma
It's a game changer.
to launch us into space. But I'm curious, when did this whole hydrogen rocketry journey actually begin? When did we first start experimenting with this stuff?
Well, like a lot of breakthroughs in space, we got to thank the pioneers at NASA.
Of course.
They took a big gamble on this, like we said, counterintuitive fuel, and, well,
What happened?
the story is full of twists and turns and dead ends, but ultimately, it's a story about some really remarkable engineering.
All right, so take us back. Where do we begin?
Our story starts with Project Centaur,
Project Centaur.
back in the late 1950s.
Okay.
Now, this was a big deal because it was the first time a rocket stage was designed to run solely on liquid hydrogen and liquid oxygen.
Wow, they really went all in on this.
They did. Talk
Yeah.
about a leap of faith, right?
Yeah, so what happened? Did it work?
Well, about that, like with any pioneering endeavor, there were some bumps along the way.
Booms.
Let's just say that those early Centaur tests were quite the experience.
Okay, you got to give us the details.
Remember those material challenges we talked about?
Yeah, the whole brittle at super low temperatures thing.
Exactly. That caused quite a stir during those early tests.
Oh, I bet. What kind of setbacks are we talking about here? Give us a picture.
Picture this. You've poured your heart and soul into designing this revolutionary rocket stage. You're ready for launch, and then crack.
No.
The metal starts to crack under the extreme cold of the liquid hydrogen.
You're kidding.
Or imagine the insulation failing, leading to a rapid boil-off of the fuel.
Oh, no.
Those early Centaur launches were a wild ride.
It sounds like they were learning the hard way.
They were. But think about it. Every failure, every explosion, it was a lesson learned. It all fed into the next iteration, pushing the boundaries of material science and engineering.
And paving the way for everything that came after.
Exactly. Those early failures, they were crucial. They led to the development of new alloys, better insulation, a deeper understanding of how to handle this insanely potent fuel.
So from those early growing pains, we got to
the Saturn V.
the Saturn V, the big one.
The legend.
The rocket that took us to the moon.
A symbol of what happens when we really push ourselves, when we aim for the stars.
And at the heart of it, liquid hydrogen.
Its second and third stages, powered by the mighty J2 engine, wouldn't have been possible without it.
It's one thing to talk about powerful engines, but let's get down to the brass tacks.
Let's do it.
Our sources mentioned something about combustion instabilities.
Ah, yes, those pesky instabilities.
That could literally tear an engine apart.
It's true. Imagine a symphony orchestra where all the instruments are playing slightly out of tune. It wouldn't sound so good, right?
No?
Well, that's what can happen inside a rocket engine, except instead of an unpleasant sound, you get these powerful vibrations that can rip the whole thing apart.
So how do you even begin to solve a problem like that?
It took a combination of, you guessed it, ingenuity and a deep understanding of acoustics.
Acoustics.
Sound waves. They developed these baffles, resonators, think of them like acoustic dampeners inside the combustion chamber.
Okay.
To disrupt those harmful vibrations and smooth out the energy flow. It was like fine-tuning a musical instrument, but with, slightly higher stakes.
Yeah, no pressure. Just the future of space exploration resting on your ability to harmonize an explosion. So we've got Centaur, the Saturn V, and we can't forget about another big player in the story of hydrogen rocketry.
The Space Shuttle.
The shuttle.
Iconic.
With those incredible RS-25 engines.
No, those were game changers. Reusable, crazy efficient, thanks to their staged combustion cycle. And get this.
What?
They could throttle up or down mid-flight, just like a car engine.
No way, really?
Yeah. All thanks to liquid hydrogen and liquid oxygen.
Wow. Throttling mid-flight.
It's pretty slick.
That's like comparing a, sports car to a horse and buggy.
Yeah, it's a pretty good analogy.
But, as with any daring adventure, there are always risks.
That's true.
And the Space Shuttle program, it had its share of tragedies.
Yeah.
Challenger, Columbia, those were such profound losses.
Absolutely. It reminds us that, even with all the technological marvels, space exploration is still a risky business.
For sure. It makes you appreciate the bravery of the astronauts and the countless people behind the scenes who make these missions possible.
Literally, they're the real heroes.
So where do we go from here? What does the future hold for hydrogen rocketry?
That's the exciting part. We're not just talking about building bigger and better rockets.
Okay.
We're talking about developing entirely new technologies to take us further, keep us in space longer, and do it all more sustainably.
Sustainability in space travel, that's something I don't think we hear enough about.
It's becoming more and more important.
So what are we talking about here? Our sources mention things like plasma-assisted combustion,
Right.
green propellants. It feels very Star Trek. Break it down for us.
Okay, so remember how we were talking about plasma being a key part of rocket exhaust?
Yeah, right.
Well, imagine harnessing that plasma, that super hot electrically charged gas, to actually make combustion even more efficient.
Hold on. We're talking about controlling the plasma during combustion.
Exactly.
Wow.
Plasma-assisted combustion could let us ignite fuel at lower temperatures, burn it more completely, maybe even use less fuel overall.
So it's like giving those engines a turbocharge.
Pretty much.
But with less impact on the environment.
Potentially, yeah.
Music to my ears.
Mm.
And what about these green propellants? Is there a way to make hydrogen fuel itself more sustainable?
That's the million-dollar question, right? Even though burning hydrogen produces just water vapor, we still need to produce and store it, and that's where things get tricky. But scientists are working on it. They're looking at ways to produce hydrogen using renewable energy, things like solar power, through a process called electrolysis.
Electrolysis.
Yeah, it's basically using electricity to split water molecules into hydrogen and oxygen.
Clever.
Right. And get this, they're even looking into bio-derived hydrogen.
What does that even mean? You're going to make rocket fuel from corn husks?
Well, not exactly corn husks, but you get the idea.
Okay.
They're trying to figure out how to create hydrogen fuel from organic matter.
So we could have a future where we're flying through space on fuel that's been sustainably created here on Earth.
It's a real possibility, and it's not as far-fetched as it sounds.
That's incredible.
It is pretty wild to think about.
It feels like we're on the cusp of a whole new era of space exploration.
I think we are.
It's mind-blowing to think that this simple element, hydrogen, the same stuff that makes up the stars, could hold the key to unlocking humanity's future in space.
It's a beautiful thing.
It really is. It makes you wonder, what new horizons will hydrogen allow us to reach? Well, that's all the time we have for today's deep dive into the world of hydrogen rocketry. It's a story of incredible innovation, relentless problem-solving, and this never-ending desire to explore the cosmos. Thanks for joining us, and remember, keep looking up.